Swayam Prabha. Digital India. Educated India.
Welcome students to Flight Laboratory. So far we have discussed thrust required, power required for a cruise. We have also discussed range, endurance. Very important thing, the takeoff and landing. So today this is a warm-up lecture for takeoff and landing. Please draw your attention to this part, which is the landing gear. Okay? And you could see this type of configurations are called tricycle landing gear, one nose wheel and two rear wheels. When we are going for a takeoff, at an appropriate speed, the nose will be raised high like this, and it will continue and lift off, and then it will do like this for a cruise. Okay? So once I am going like this, I have started the engine, got a particular speed through acceleration, and then I will pull the elevator, and elevator will go up. That will make the aircraft roll slightly like this, and then continues flying, climbing, and after that again I make the neutral position of the elevator or to a desired elevator position. Basically I am now reducing the elevator angle and I maintain a cruise. Why all these things? Why I try to lift the nose up? Because I want to get lift. Because for takeoff, I need to have lift little more than the weight, or at least lift equal to weight. Okay? Now, for getting that lift, I need angle between the airplane and the velocity vector. That is why I have to roll this airplane for a tricycle landing gear configuration. Okay? This is one part. I have been mentioning at a particular speed it will roll the airplane. And how do the pilot know about the speed? For that we have got an initial briefing about airspeed indicator and Peters tube. We will have more discussion on aircraft instrument in a detailed manner. Maybe 2 lectures will be dedicated on that. Just for completion, you could see here it is the Peters tube. Okay? And you could see there is a hole here. Here all the air goes inside and pressure total goes to the airspeed indicator. You see the static points here. From here the static pressure input goes to the airspeed indicator, and you know there is a diaphragm and the differential of total pressure which is inletted through this point, and the static pressure from here it goes to a diaphragm, and because of difference in pressure the diaphragm will contract and do like this. Accordingly this motion is translated through a lever and you get the readings. Okay? It needs some calibration, but important thing is before you are going for a flying, because you need to know what is the speed. For a pilot, speed is extremely important. So one has to be doubly sure that the Peters tube is working. That is, sometime what happens, some insects may lie inside this Peters tube and actually may be getting a wrong value. So very, very dangerous situation. So any pilot, before he takes off, he will ensure, despite the engineer's clearance, he will check the Peters is working or not. Okay? In addition to other control surfaces. But this is extremely important. Please understand. That's why I am over-stressing. So for a takeoff, I need to have correct speed and correct orientation. That is the main thing. Now let us see another type of landing gear which I will be showing there. We were showing tricycle type landing gear, but if see this is airplane, this Piper Super Cub, one of the very powerful airplane. We have been using it for more than 40 years. Now this is grounded and we are using it for static demonstration. You could see here, this is not a tricycle type landing gear. This is basically a tail dragger. There is a tail wheel landing gear there and 2 here. Okay? What is the difference between this configuration and the tricycle configuration? You could see even at this position, this wing is making an angle of attack with the velocity vector. If it is going straight, there is the angle of attack. So now when we are going for a takeoff, already it has got a high angle of attack, but the moment I try to start the engine and try to do taxiing, this will produce a lot of drag. Okay? So what is done, when the pilot is taxiing this airplane, at some speed, he will use the elevator and take the tail portion up. So it will become almost horizontal like this. Okay? So nose wheel touching the ground and the tail wheel will be little up. And then at an appropriate speed when he reaches, then he pulls up and goes. Because advantage is this wing is having already some angle of attacks with respect to the horizontal. But why all these things? Please understand, finally to take off, I want to take off at a lowest possible speed. And that you know by now, that is possible when the CL max is large. That means for a pilot, theoretically speaking, he will try to fly at an angle during takeoff which corresponds to near alpha stall, that is near CL max, which generally may not be really realistic. So what is done? You try to fly at a high angle of attack. In a sense, compared to 2-3 degrees, you try to 8-9 degrees and have sufficient speed and you go for a takeoff. Before I end, I want to stress another point as per the landing gear is concerned. Remember, for all this tricycle landing gear, we have understood why the CG should be little ahead of landing gear. Otherwise, this tail will hit the ground. But for a tail dragger, the CG is behind this landing gear part. Okay? So that is why if you ask many pilots, although they enjoy flying this machine, but they also have a reservation about crosswind performance, especially during landing. It is something like driving a car with the engine at the back. You have to fly like this. Well, barring that, it was a very popular configuration, and many years this configuration was in existence. I am sure there are many pilots who love this configuration. I personally love this airplane. Okay, thank you. So far we were demonstrating you the landing gear, their orientation. We talk about tricycle landing gear, we talk about a tail dragger, and we have realized that we need to generate sufficient lift, preferably more than the weight, to leave the ground. Okay? Now the question comes, when I try to think of takeoff distance, let's say we are talking about takeoff distance, what should be our aim? Our aim should be that I should be able to design an airplane which should not take much of takeoff distance. If you say the distance is too large, then who is going to give you the land? Land is so costly. So one extreme is vertical takeoff or vertical landing, the VTOL. But we are talking about fixed wing so far that we have been successful in ensuring that this takeoff distance is as low as possible depending upon the technology available. How it is done, that exactly I will be discussing. If I recall this CL versus alpha, and this was marked as CL max and this was alpha stall. Loosely, what was the meaning is, if you are flying at alpha stall, you are likely to get maximum lift, but slight disturbance, slight more than the alpha stall, you are going into a stall and you don't want to fly in stall because lift reduces, drag increases, other complicated thing happens. So mostly you try to fly somewhere here, right? Okay. So that is the maximum value you can really get. And theoretically speaking, we say CL max, which is this point, but the maximum CL we are getting here. If I could somehow theoretically get CL max very large, then the Vstall will be less. Why? Because we know lift equal to weight, so V equal to 2 W by S rho CL under root. If CL is CL max, then this is Vstall. Okay? What is the message here? Message is very loud and clear. This is the minimum speed with which the airplane can fly for a given wing loading and given density, that is given altitude. Because this is the you have maximized the contribution of lift coefficient CL max, right? But I repeat again, pilot will not like to fly at that CL max, because if there is slight disturbance, he may dip into a stall. So he will be flying a little less, maybe 20% less than CL max, which is practical. So if I want to reduce Vstall, if I want to reduce it, why I should reduce? Because we are talking about takeoff, okay? That is, I am starting from V equal to 0 to V takeoff. We will let you know what is this takeoff. It will be 10 to 20% more than the Vstall, and it goes up. If I want this distance to be smaller, what are the options I have got? I have got put an engine which is having very high thrust to weight ratio, because this is responsible for acceleration. This is T is thrust. Loosely we say high power engine. Right? Then if it accelerates very fast, then it takes smaller distance to get to V takeoff. If it is a lowly power, then it will take longer distance. So one way, you increase the T by W as high as possible, but then there is a problem. The moment you want to put a high thrust, high power or powerful engine, the weight may be a penalty, but there is a limit for engine. So what is the approach? Yes, whatever best one could do for T by W will do in realistic manner. However, from whole aerodynamics point of view, or more precisely by taking the advantage of aerodynamics, we can still reduce this distance. How that could be reduced? That could be reduced if I reduce Vstall, that is minimum speed the airplane can fly, and to reduce Vstall I have to increase CL max. The message is clear. If we want short takeoff distance, then reduce this Vstall. To reduce Vstall, what I could do for a given wing loading and altitude, I have option of increasing CL max. So then now the question comes, how can I decrease Vstall? That is the question. So to decrease Vstall, one thing we have realized, I have to increase CL max. Second thing, if I want to decrease Vstall, there is another very important parameter sitting here, is wing loading. So if I want to decrease Vstall, what I have to do with wing loading? I have to reduce wing loading. And reduction of wing loading means what? If you want to reduce this, like CL max, reduce Vstall further, I have to reduce the wing loading. Reducing wing loading means what? I have to increase the wing area. Okay? So keep this in mind. This is important. And we will use this concept. Use this concept. Okay? It's very important. Let's not lose insight. Please understand again. We want to reduce the takeoff distance. To reduce takeoff distance, we have understood the Vstall, or the speed at which lift equal to weight, should be low. To ensure that Vstall is low, I have two options. One is I should increase CL max, or I should decrease W by S, or I do both the thing, that is increase CL max and decrease W by S. If I could do that, I will be able to reduce Vstall, and immediately you will see that the takeoff distance will reduce. Okay? Let me also further stress on Vstall. Classically, when we are talking about Vstall, we are talking about, the situation where this lift equal to weight and of course thrust equal to drag, right? That is how we write V is equal to, or you write L equal to W, so V equal to 2W by S rho CL. Okay? And for V stall, we write here, this is CL max. No issues? This is a classical definition of V stall. But in practice, what happened? It's not that pilot is always doing cruise. He does maneuver. Okay? That is, he will be, let's say he's taking a turn. This is the lift. And let's say this is the weight. And this is phi. You know that L cos phi and is equal to W. That is, he's trying to take a bank turn without losing the altitude. He's not doing this. He's doing this. So this is a turn maneuver. Here I see L by W is 1 by cos phi. By now you know this is N, called the load factor. For lift equal to weight, or for a typical cruise, N was equal to 1. And for a maneuver, this N is 1 by cos phi. That is, suppose bank angle is 60 degrees, then N is around 2. Right? That is 1 by cos 60. Cos 60 is half, so this is equal to 2. You understand the meaning of load factor 2. Now you see, if this load factor is 2, and if I ask you a question, what is that minimum speed with which I should fly the airplane so that I can manage this turn maneuver? Then your practical definition can be upgraded, and you see it is N W by S by rho CL max. That is because lift equal to NW now. Are you clear about it? If we are doing a turn maneuver, then lift is no more equal to weight. Lift is NW. Okay? And if I use the relationship, I can find the minimum speed, and I'll call it stall speed for maneuver is N W by S by rho CL max. And now I could see that V stall maneuver, VSM, is root of N V stall cruise. Let's try to understand this physically. Suppose pilot is going like this, and there is some necessity for him to turn like this, go this way. So what he does? He banks, and then he turns like this. Okay. Now, as per this relationship, that the minimum speed should be Vs, which is more than the classical V stall speed. By how much? By root of N. So this gentleman, VSM, is greater than Vs cruise. That means when I am trying to bank and turn, my stall speed to maintain that maneuver, my minimum speed to maintain that maneuver will be more, and my engine must have enough power. Or if I am not utilizing the engine power, or I am already at the threshold of engine power, then I should have enough lift to produce that load factor. And in that process, in the confusion, what can happen? The pilot may go on increasing the angle of attack, and he may go into a stall unless the aircraft is properly designed. That is why the VSM stall speed for maneuver is so important. A designer must ensure that within the flight envelope for different N, the pilot in command should be able to generate this much of load factor without going into stall. Right? This is extremely important. Many accidents happen because of this confusion. Okay? So if I summarize, what you have seen, V stall is 2 N W by S by rho CL max where for n equal to 1 is our classical Vstall, which is 2W by S by rho CL max. Also we have seen Vs for maneuver is root of n into V stall cruise based on the cruise. Okay? Now here also you have seen that L by W is cos phi. Just to give you a feel, you can check yourself if it is 10 degree, 20 degree, 30 degree, up to 60 degree. You could see from, and phi equal to 0 degree, from 1 to 2, this load factor changes. And that's an appreciable change, right? And one has to be fairly cautious. A designer has to be fairly sincere and systematic to ensure that the pilot has this bandwidth. He can do a bank and he gets enough power, enough CL without going into all those troubled area. Okay?